In the beginning, the universe was thought to be a vast, still stage, a grand, unchanging theater of stars and planets where time ticked forward like a universal clock. This was the world of Isaac Newton, where space was the emptiness in which matter moved, and time flowed independently of everything. For centuries, this view held strong. But in the early 20th century, a young patent clerk named Albert Einstein peered deeper into the fabric of the cosmos, and what he found unraveled reality itself. Einstein noticed a mystery. The speed of light was the same no matter how fast you were moving. This defied intuition. If you chased a beam of light, shouldn't it seem slower? He dared to imagine something radical. What if time itself could bend? In 1905, his theory of special relativity was born. It told a stunning truth. Space and time are not separate, but fused together into a single entity. In this new reality, time could slow down. Lengths could contract. Events could shift in order depending on who was watching. Two travelers, moving at different speeds, could live different timelines. The universe was no longer absolute. Space-time was relative. But that was just the beginning. A deeper question loomed: what is gravity really? For Newton, gravity was a force that pulled. But Einstein saw something more beautiful. He imagined a massive star or planet sitting in the fabric of space-time. And he pictured the fabric bending, like a ball sinking into a stretched rubber sheet. In 1915, he unveiled general relativity, a masterpiece of geometry and physics. Its central idea was simple, yet profound. Mass tells space-time how to curve, and curved space-time tells matter how to move. Suddenly, gravity wasn't a force at all. It was geometry. A planet falls not because it's pulled, but because it follows the natural curve of space-time around the sun. These paths are called geodesics, the straightest possible lines in a curved world. Einstein's equations were powerful, too powerful. They predicted places where space-time could twist into knots, where gravity became so intense that not even light could escape. Black holes. At first, many doubted such monsters could exist. But eventually we saw their fingerprints, stars dancing around invisible giants. Ripples in space-time, gravitational waves, echoing from cosmic collisions. These were no longer just equations. They were real. Meanwhile, the universe itself was not sitting still. Edwin Hubble discovered that galaxies were racing away from us. The fabric of space-time was expanding. This expansion had a beginning. A moment when everything was squeezed into an unimaginably small point, the Big Bang. From that first instant, space and time were born. Every second, the cosmos stretched wider, like ink swirling in water. And it hasn't stopped. But what drives this expansion? Here, Einstein's forgotten idea returned, the cosmological constant. A mysterious force, called dark energy, pushes space-time outward faster and faster. Deep within atoms, space-time becomes fuzzy and uncertain. Gravity clashes with the rules of quantum mechanics. In this strange realm, physicists chase new dreams. String theory, where particles are tiny vibrating strings, and space-time has 10 or 11 dimensions. Loop quantum gravity, where space itself is made of loops, and time may not be fundamental at all. At the Planck scale, unimaginably small, space-time may not be smooth, but granular, like pixels on a cosmic screen. Einstein once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." In modern physics, many believe all of time, every second that ever was or will be, exists at once, like pages in a book. The present is just the page we are reading. This idea, known as the block universe, suggests that our journey through time is like tracing a line through an already painted canvas. Space-time doesn't just evolve,